Hi, this is TheoryStation. I'm John Duggan, and this is the Rational Choice Modeling Program. The series is cost-benefit analysis. This is the first installment in the series, and I'm going to just talk about the basic cost-benefit model. And give some kind of simple background conditions to make the model usable, and just to go through some examples of actually solving it and applying the model. So I want to touch on several issues. Well, let me give before I go to the issues, let me just present the model. So so here we have a decision maker who chooses the scale of some project. It could be, you can think of it in different ways. It could be an effort that's exerted. It could be actual resources that are, directed toward this project. Whatever that scale is, I'm going to denote it by X, and it's going to be a non-negative number. And then given X, there's going to be some benefit that's generated by that scale. And then there's going to be a cost. That is entailed by X. As far as the units that we're measuring these in, you can, in a lot of applications, they would be measured in dollars. The main thing is just to, they have to be measured in the same units so that we can take the difference between them, and we'll call that the net benefit. That's just the benefit minus the costs of the scale. So, right, the whole problem here is to choose X to maximize net benefit, or written in a more mathematical way, we're going to solve this optimization problem where we maximize benefit of X minus cost of X. Okay. And we call that net benefit, we'll call that the objective function. And that's what we're trying to maximize here. Okay, so I want to talk about several different issues. Let's boil it down to three. The first is, if you're using this model, you can use it in different ways. I mean, one way is a kind of normative way. So you want to recommend a scale of this project to a decision maker. You're basically you're solving this optimization problem to see what they should choose. A different use of this model would be to use it in a positive or predictive way, where you're going to predict that the decision maker chooses X in an optimal way to maximize net benefit. In either case, there's a question of, is there an optimal scale? Okay, so existence of an optimal scale. If there is no optimal scale, this model is not going to be very useful. So I want to talk about just basic conditions for existence of an optimal scale. There's a question about uniqueness of the optimal scale as well. Okay, that is, can there be more than one optimal level of X? The last issue is kind of a combination of two, but it's convenient, or I'll say we can use calculus methods to characterize the optimal scale when it happens to be a positive amount. Okay, so So the last issue is, when is the optimal scale positive? And then given that, we want to use calculus methods to characterize what that actually is. Okay, so I want to touch on those issues. As far as existence goes, it's easy to come up with examples where there is no optimal scale. But let's actually impose a little bit of structure to begin that will simplify the analysis for us. So let's assume that the benefit and cost functions are continuous, and more than that, they're actually differentiable. Intuitively, that just means that they're smooth functions, and if you think about the graph of the function, at any point there's a well-defined tangent, and the slope of that is going to be the derivative of the function, which lets us use calculus methods. Okay, so then we can take the derivative of the benefit function, let's say, at any scale, and that's going to tell us how the benefit is increasing as we make x bigger. And this is called the marginal benefit at x. And sometimes we'll use this notation MB for marginal benefit. Cost is the same convention, so C prime will be the derivative of the cost function. We call that the marginal cost at x, and we might use this MC notation for that. Okay, at this point I should to be a little more technically precise, I should point out that there might be some applications where the benefit function is only defined on positive scale levels. For example, suppose the benefit function has the natural log form. That's kind of nice to work with in some applications. The natural log function is only defined for positive x. That's okay. For what we're doing, we can admit those functions as well. When we're talking about derivatives of the benefit function, we're really only focused on derivatives when x is positive, and so this isn't really an issue. Okay, so that's just an aside. So now that we've assumed that these functions are differentiable, it's still not quite enough structure, because this would still allow a benefit function that looked like this, for example, and a cost function that looked like this. And these are kind of weird functions. For one thing, as x is increasing, so here the horizontal axis represents different scales. The vertical is whatever the units are we're measuring cost and benefit in. Notice that as we increase the scale, the benefit from that increases, but then it goes down. Now that's not logically inconsistent, but in most of the applications where we want to apply this, this scale or effort is a good thing, and the more of that you have, the higher the benefit. So really, we want this benefit function to be increasing, and let's let's assume, we'll state that in calculus terms, and we'll state a strong form of it. So let's assume that for all x, that derivative is strictly positive, okay? As well, let's assume marginal cost is strictly positive. That rules out the picture that I just drew. Now the benefit function has to be strictly increasing. The cost function has to be strictly increasing as well. Okay. Notice though, the way I drew these, they're still kind of wiggling. Okay. And again, there's nothing inconsistent about that, but in a lot of the applications that we're thinking of, the natural assumption is that these benefit and cost functions have a nicer kind of curvature. Okay. So we're going to focus on benefit functions that have this kind of concave shape, okay, and cost functions that have this kind of convex shape. Okay, so we're going to split this assumption up into two parts. As far as the benefit function goes, notice that the derivative of this thing is getting, well, the slope is getting flatter and flatter as we choose higher scales. So the derivative is getting lower and lower. And so in calculus terms, the way we would write that is that the second derivative of the benefit function is negative, or I'm going to say at least not positive, okay? For the cost function, the situation is kind of the opposite, where as the scale increases, the slope is getting steeper, so the marginal cost is increasing, and so we say for all x, the derivative of marginal cost is positive. I'll write that with a weak inequality. Okay, so we're basically saying the derivative of the marginal benefit is negative, or at least not positive. The derivative of marginal cost is positive, or at least not negative. Okay. I've written these with these weak inequalities here. But let's add one more assumption that at least one of these is strict. Okay. The reason why I'm doing this is because I mean, it wouldn't be so bad to just assume strict inequalities, but then that would rule out a situation with a linear benefit function. Okay, like this. For this linear benefit function, the slope of that doesn't depend on the scale. So if I were going to draw the marginal benefit function, it would just be a constant, okay? Here I wrote MB for marginal benefit, but we can write B prime too if you want. So here, in this example, the second derivative of the benefit function is 0, right? Because the B prime is positive, so the derivative of that is just, sorry, B prime is a constant, and so the derivative of that is just 0. So, you know, if we use strict inequalities here, we would rule out some nice examples, and let's just not do that. So we'll allow for weak inequalities, but I will assume that one of them holds strictly. So we cannot have both of these functions being linear. So this first part here is saying that b is a concave function. There's actually a more general definition of concavity, but for differentiable functions, this is what concavity means. It means the second derivative is non-positive. The second part of this assumption is that c is a convex function. Okay. Again, there's a more general definition, but for differentiable functions, convex means that the second derivative is non-negative. We're going to assume that benefit is concave, cost is convex, but at least one of them is strictly so. And those will capture really most of the applications that we would want. Okay. All right, so where are we then? We've imposed more structure on this problem, and I want to go back to the existence question. When does there exist an optimal scale? Well, in these pictures, in all the pictures I've drawn so far, there is an optimal scale. Just to be a little more systematic about, the geometry of the optimal scale. If you have a benefit function like this and a cost function like this, the net benefit is the difference between these two functions, okay? So here's an x prime, let's say, and the net benefit is the height of that dark line segment. Here is an x double prime. The net benefit is the height of that dark line segment. But you can tell that the net benefit is not maximized at either x prime or x double prime. It's going to be maximized something, somewhere more like this. Okay, it looks like the net benefit is just about maximized there, and we'll call that x star. Okay, so there's a case where there's an optimal scale, and we can kind of figure out what it looks like there. It turns out, though, that this kind of basic structure that we're imposing is not enough to ensure the existence of an optimal scale generally. Okay, this is just one picture where there is one, but we can draw another picture where there's not. Okay, so the way I'm going to draw this is I'm going to draw two lines that are parallel. Okay, and now the benefit function is going to increase. It's going to go above that dashed line, and so initially when it crosses the dashed line, the slope is higher than the slope of the dashed line, and I'm going to have that benefit function get flatter and flatter. It's going to have this concave shape. I want you to imagine that the slope of the benefit function is always greater than the slope of the dashed line, but that it's getting closer and closer to the slope of the dashed line. Okay, so because it never actually goes, because the slope of the benefit function never actually goes back below the slope of the dashed line, it's going to stay above it forever. Okay, and then I'm going to do the same thing for the cost function. Okay, it's going to cross that lower dashed line. It's going to start getting steeper and steeper. The slope of the cost function, though, is always going to be less than the slope of the dashed line. It's going to get bigger, but it's never going to get back up to that slope. Okay. I don't know if that's clear, but in this example, the difference between the benefit and cost, that is the net benefit, just gets bigger and bigger and bigger as you increase the scale. Okay, so here there is no optimal scale. You would just want to choose arbitrarily an arbitrarily high scale. It can't be big enough. Okay, so this is a situation where the cost-benefit model doesn't work very well. So we just want to understand what kinds of conditions will rule that out, and then we can, when we're applying the model, we can make sure that we are focusing on cases where the model actually is useful and actually has an optimal scale. So this is actually a simple problem, honestly. So we'll assume really the problem here is that for all x, the marginal benefit is greater than the slope of the dashed line, which is greater than the marginal cost. Okay, that's what's driving the problem here. That means that the difference between benefit and cost is getting bigger and bigger as you make x larger. So what we're going to do is just assume there's some scale such that this doesn't hold, okay? And so for big enough x, for a high enough scale, marginal benefit is less than marginal cost. If that's true, then that means that, I don't know if I can fit it into this little picture here, but if this is our marginal cost, sorry, if this is our cost function, and this is our benefit function, then if I go out to, let's say this x here, you can see that the marginal cost, that's the slope of this tangent line, is greater than the marginal benefit, which is the slope of the tangent line to b here. And if I draw that a little bit better. So what that means is that, because the benefit function has a concave shape, it's always going to, if I extend that tangent line, the benefit function will always be below that tangent line. If I extend this tangent line down here, the cost function will always be above that. Eventually, those are going to cross. This is not quite, it's too small. Let's make a bigger picture. Okay, so so here's our benefit function. Here is our cost function. Here is an x where the marginal cost is bigger than the marginal benefit, right? Let me just continue these dashed lines, continue the tangent lines. Eventually, somewhere they're going to cross. Okay. Now, what do I know? The benefit function, it has a concave shape. So as I go out beyond x, that benefit function will always stay below that tangent line. Okay. The cost function will always stay above the lower tangent line here. Because those two tangent lines cross out here, that means that somewhere before that, the benefit and cost functions must cross, and that's right here. Okay. So at that point, I think it should be pretty intuitive. Let's say where they cross, let's call that x bar. Okay. At that point, the net benefit is 0. And then for any higher scale, the net benefit is actually going to be negative. Okay. And, you know, that's clearly it's not going to be optimal to choose something out there. So if we focus then on scales here between 0 and x bar, that is that's an interval that's bounded, and in the terminology of mathematics, it's a compact set. The net benefit is a continuous function. It has to achieve some maximum. And I think that if you're just looking at this picture, you can just see that somewhere in here, the height of that distance between the benefit and cost function is going to have to be maximized. Okay, there is a theorem in real analysis that actually tells us this in a very formal way, but what we have to take away is just that as long as there's some point where marginal benefit is less than marginal cost, this problem will have a solution. Okay. I should say that I gave a condition, right? There's some x where marginal benefit is less than marginal cost. Another condition that's used is it's called the Enotic Condition. It's actually a family of conditions, but you'll see some papers that will assume something like this. They'll say, if you look at the marginal benefit, eventually they'll assume that the benefit function, eventually the slope is getting very close to 0. It's getting close to flat. And the way that's expressed is you say the limit of the marginal benefit as x becomes very big is 0. And then that's paired with another condition that says the marginal cost, as you choose a very high scale, starts to become arbitrarily big. And the way that's described is that the limit of marginal cost becomes infinite as the scale gets big. Okay. So this Enotic condition, it's stated in terms of these two limits. We don't have to go into the exact meaning of what these limits, how they're defined, but this is a much stronger condition than what we just talked about. Obviously, if the marginal benefit function is getting very flat and if the benefit function is getting very flat and the cost function is getting very steep, then eventually at some point, marginal cost is bigger than marginal benefit. So this is stronger than what's needed for existence. But it's a term that you might see. Okay, so we've talked about existence. The next issue is uniqueness, and unfortunately, that's not really an issue for us. So with the structure that we're imposing on the problem already, if there is an optimal scale, it's unique. Okay, so it wouldn't be a huge problem if there were more than one optimal scale, but this is something that you just like to know. So then we can refer to the optimal scale. It just simplifies things a bit. The last issue that I wanted to talk about is about interiority of the optimal scale. That is, oh, and by the way, I'll just use the notation because we now have conditions under which the optimal scale exists. We know it'll be unique. I'm just going to use this notation for that optimal scale x star. Okay. So now the next question is, when is that optimal scale actually strictly positive? Okay, so it's been, in every picture I've drawn, if there's an optimal scale, it's positive. So what are we actually concerned about here? Well, we're concerned about something like this, where the cost function is like so, and the benefit function is like so. Okay. Here, the benefit function is nice and concave. The cost function is nice and convex. But if I pick a scale like this x, well, cost is higher than benefit. So the net benefit of that scale is negative. Okay. More to the point, if I choose a smaller scale, it's still going to be negative in this picture, but at least it's not, it's smaller in magnitude. So, let's call that x prime. In this picture, the net benefit from x prime, even though it's negative still, at least it's bigger than x. Okay. But then actually, if I just choose a smaller scale, the net benefit's going to be bigger than x prime. In fact, in this picture, this is a long-winded way of saying that the optimal scale is just 0. Okay. There's nothing wrong with that. It's perfectly possible that you have an application where the optimal scale is 0. But it's nice to understand when we can ignore that kind of situation, because this actually will, I guess, to deal with these kinds of, they're called corner solutions, you have to deal with them separately from the positive case. For the positive case, we can use calculus techniques to understand the optimal scale. And so we want to just have, we want to be able to separate these two situations. So the question then is, under what conditions, that is, what kind of structure can we impose on the model that will rule out this corner solution, okay, and give us a strictly positive optimal scale? Well, it's probably fairly clear just from looking at this that in this picture, what's driving this is that if I look at the slope of the benefit function at 0, I don't know if that looks quite right. Try again. It's like this. If I look at the slope of the slope of the benefit function at 0 is the slope of that blue line. For the cost function, the slope at 0 is the slope of that red line. You can see that the marginal cost is always bigger than marginal benefit here. Okay, so what we'll do is we'll assume that for some scale x, that marginal benefit is strictly bigger than marginal cost. Okay. In fact, there's a stronger condition that's used sometimes, and it falls in that Enotic family of conditions. Stronger condition that's used is that that the marginal benefit for small scales becomes very high. So the way that's expressed is in terms of a limit. As x goes to 0, that marginal benefit goes to infinity. So if you're drawing a graph of the benefit function, as you're getting close to 0, the benefit function becomes arbitrarily steep. That would be satisfied by functions with a power form, right? Because then marginal benefit would be, and if here beta is between 0 and 1, right, then the marginal benefit would be beta times x to the beta minus 1. Well, beta minus 1 is negative, so we can write that as this. So here, as as x is getting very small, we're dividing by something that is close to 0, and that thing will blow up and go to infinity. And that is paired with the assumption that marginal cost becomes very low for small scales. And so we write that in terms of a limit like so. All right, so that means marginal cost is coming in and getting very, very flat. And that's also satisfied by power functions like x to the gamma, where gamma is bigger than 1. Okay, so this, again, it's in this family of Enotic conditions. And you can see that it's stronger than what we just assumed. We're assuming that there's some x such that the marginal benefit is bigger than the marginal cost. Okay. So with this Enotic condition, when x is small, this marginal benefit's going to be becoming arbitrarily big, and the marginal cost is going to be going to 0. So obviously, this inequality will hold for small scales. So anyway, that's just a stronger condition that's used, and it just might be something you run into. Okay, so that's enough for the setup of the basic model. I didn't get into actually solving any examples of this and showing how that's done. So in the next installment, I'll be talking about the first order approach to actually solving these problems, and that's what's coming up. I'll see you in the next one.